robot adventures.
Okay, hello everybody. My name is Jim Bai. Today I want to give a talk about robot navigation using velocity, potential field, and particle filters for obstacle avoidance. First, I want to give a brief introduction about our research object and the research approach. Our research project is to find proper turning direction to avoid obstacles and reach the goal based on the local map robot build. And the second research project is to obtain estimated robot position based on the measurement from obstacle and the goal when showing in robot searching range. And for our research approach, obstacle avoidance algorithm is derived from velocity potential field method. And estimation regarding to robot position and obstacle positions are based on the particle filter based FastLab approach. Here I want to give some background information. Mobile robots are used in military, industry, and field circumstances. And autonomous robots are the robots with a high level of autonomy and are capable of intelligent motion and action without requiring a wireless guard to or teleoperator control. And motion planning is composed of 4 parts: navigation, coverage, localization, and mapping. And simultaneous localization and mapping, which is called SLAM, which is our major research field, is the computational approach of constructing or updating a map of unknown environment while simultaneously keeping track of the robot location within it. Here is a modified velocity potential field method. In this method, we will use 2 velocities. One is attractive velocity from the goal, and the other one is the repulsive velocity from the obstacles. Actually, the repulsive velocity is composed of 2 parts. One is a normal one, and the other one is tangential one. The overall velocity we use in our research is a vector summation of all these 3 velocity vectors. And here I want to give an introduction about the robot with its sensor configuration. As we can see in figure 1, the outermost circle means the searching range of the robot, and the inner one means the safety range of the robot, which means when the obstacles enters into this safety range, the robot will be applied to obstacle avoidance algorithm, try to avoid them. And figure 2 shows the case when the robot met the obstacles. And we can see when the robot met the obstacles, it will obtain a local map, which is showing here. Actually, the intersection point with the sensor beams and the obstacles. And we can see this local map is composed of 2 parts. One is regard to the yellow section, and the other one is regard to the green one. So we can see in this case, the local map with regard to the yellow section has a bigger dimension than the red ones. So in this case, robot will turn right, try to avoid the obstacles, and finally reach the goal with efficiency. And the FastLab approach is a factored solution to this SLAM problem. And its algorithm obtained the estimation of the full posterior over the robot pose and the obstacle locations recursively. The FastLab approach is derived on the Bayesian point of view, which is shown in figure 3. And this equation is the mathematical equation of the FastLab approach. I don't want to spend time to explain it. And now I will give the principle of particle filter method. Suppose we have a nonlinear system, and we will produce the particles based on the probability density function of the system equation. We can see here the plus superscript means these particles are obtained when we have the measurement including up to and including time k. And the minus superscript means these particles were obtained based on the when we have the measurement before the measurement before time k. And after we obtained, we produce the initial particles based on the probability density function of the initial system state. We can obtain the prior particles based on the system equation right here. then we can obtain the weights for each particles based on this equation. After we obtain the weight, and we need to normalize the weight to get the normalized weights for each particle. And now we form a set of particles with normalized weights. The next step is we need to resample them to form a new set of particles with the same weight for each particle. Actually, the rule of resampling step is we propagate particles with higher weights and diminish the particles with smaller weights. The more weights the particle have, then the more offsprings it will have. And after we have the particles after resampling, and we do time propagation using the system equation right here. And we will do this process recursively. Now it's time to obtain our own system model. We will choose the position of the robot as the system state. Here, xk is a typo. It should be the bold one. That means the vector of this state. And we also have a measurement state, which composed of two parts. One is the distance from the robot to the closest obstacles, and the other one is the angle of this beam, chosen beam. Now it's time to form our own system model. This system equation set were obtained based on the velocity potential field approach, and the first equation is formed with some white noise, which is omega k, and the second equation is the measurement equation. After we obtain our system system model, we can obtain the estimation of robot paths, robot positions. The same thing, it's just like what we have talked about before, how the particle filter works. We first produce some initial posterior particles, and we do time propagation based on the system equation, and we obtain the weights for each particle. Then we normalize and resample them. We need to mention here, since we have two measurements, and so the overall weights we need is a production of two weights. The first weight is obtained based on the first measurement, and the second one is based on the second measurement, the angle. And we do this process recursively to get the estimation of the robot paths. And after we obtain the estimation of robot paths, we can get the estimation of obstacle positions based on the measurement from the robot to the obstacles. In our research, we assume we know the absolute position of the goal and the initial robot position, but we do not know where the obstacle is, so which means we do not know the absolute position of the obstacle in the global system. So the particle filter we use the Bayesian equations and measure the relevant distance from the robot to the obstacles to obtain a local map of the visible part of the obstacles. And here is our simulation results. We just test our proposed equations models in these two typical navigation environment. The first one is composed of two obstacles, where one is much bigger than the other one. Then when the obstacle go close to the obstacle, it will choose proper turning direction to avoid them and finally reach the goal. And the second navigation environment is a concave obstacles, which is composed of five small obstacles. It's a configuration obstacles. And still, the robot will find the proper turning direction to escape this concave obstacle and reach the goal. And this figure shows the simulation results with the robot traveling around two obstacles with the fast-snap approach. We can see here, the blue solid square means the estimation of robot positions with regard to the measurement regarding to the obstacles. And this blue pentagram means the estimation of robot positions with regard, based on the measurement with regard to the goal. And this blue asterisk is